Section 6.3 on the trigonometric functions of angles kind of goes along with section 5.2, which was on the trigonometric functions of real numbers. So a lot of what we're going to do here is going to be a quick repeat of things we've already done. So let's do a little bit of a review. We're talking about the trigonometry of right triangles. And you already know that if you have an angle marked theta, this is a side opposite, this is the adjacent, and this is the hypotenuse. And so your 6 trigonometric functions of theta are opposite over hypotenuse, so cosecant is hypotenuse over opposite. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. And tangent was opposite over adjacent, so cotangent is adjacent over opposite. If I put this circle or this triangle in the unit circle, instead, I'm going to call the sides of the triangle x, y, and r, where r is the radius of the circle and it's the hypotenuse of the triangle. X is a side that lies along the x-axis because when we draw triangles in the unit circle, one side of the triangle in question will always lie on the x-axis. The other leg is parallel to the y-axis, which is why we call it y. And theta is always the angle between the terminal ray and the x-axis. So the definitions now are sine is y over r, so cosecant's r over y. Cosine is x over r, so secant is r over x. And tangent is y over x, which is x over y when you're looking at the cotangent. Since r is the hypotenuse, the definition for finding sides of right triangles, normally we use that a squared plus b squared equals c squared. Well, when we use x, y, and r, it becomes x squared plus y squared equals r squared. So r, the hypotenuse, is always the square root of x squared plus y squared. The other thing we talked about is how you're going to know when your different trig functions will be positive or negative just by what quadrant it's in. And we had that little acronym. Let's try that again. All students take calculus, where in quadrant 1, all 4 trig functions are positive. In quadrant 2, only sine and its reciprocal are positive. The other 2 are negative. In quadrant 3, only tangent and its reciprocal are positive. The other trig functions are negative. And in quadrant 4, only cosine, and its reciprocal, darn it, I'm having a hard time here, cosine, and its reciprocal are positive. All the rest of the trig functions are negative. We're going to do some work in degrees here, which is often easier for students than working in radians, but radians are the more important angle measurements to learn. So just as a reminder of what we were doing when we were doing this with radians, I want to find the cosine of 135 degrees and the tangent of 390 degrees. So let's start with this. Where is 135 on the coordinate plane? Well, that's easy. It's in the second quadrant. So in the second quadrant, are cosines positive or negative? It's going to be negative. All right, negative what? Well, in order to find the cosine, I'm going to need to know its reference angle. The reference angle is the number of degrees between it and the x-axis. Well, the terminal ray is at 135 degrees. The x-axis is at 180, so the reference angle is 45. Wait a second, I know that when I have a 45-degree angle, this is my ordered pair, which is cosine theta, sine theta. So I'm in the second quadrant. The cosine is 1 over the square root of 2, so the answer must be negative 1 over the square root of 2. If you really feel the need to rationalize the denominator, you could tell me the answer is this, but either way is fine. Now let's do B. Where is 390 degrees? Well, in order to find 390, you start at 0, and then you go all the way around. You're at 360, and then 390 is going to be up here. So we're in the first quadrant, and in the first quadrant, tangents are positive. So I know the answer is going to be positive. Next, what's my reference angle? Well, if this is 360, and I want to be at 390, this must be 30 degrees. Oh, 30-degree angle, I know its ordered pair is the square root of 3 over 2, comma 1/2. Tangent is sine over cosine. So the answer is going to be 1/2 over the square root of 3 over 2. The 2's cancel and you're left with 1 over the square root of 3. Or if you'd like to rationalize the denominator, it's the square root of 3 over 3. Let's find reference angles. Remember I said reference angles are pretty easy with radian measure because the reference angle is just pi over the denominator. So the reference angle for 5 pi over 3 is just pi over 3. But let's go about this the longer way. It's easier to work in degrees. So 5 times 180 divided by 3 is 300. So 5 pi over 3 is 300 degrees. Where is 300 degrees located? Well, 300 degrees is going to be located here in the fourth quadrant. Here's my triangle. The reference angle is theta. Well, if the terminal ray is at 300 and this is 360, the difference between them is 60. What is 60 in radians? Pi over 3. Now let's go and do theta equals 870. That one's a little bit harder because you kind of have to think, well, where is 870 going to lie? I need an angle that's between 0 and 360 to do this. Well, let's find a co-terminal angle that actually lies between 0 and 360. That's going to make it easier to find the reference angle. So I subtract one circle, and I'm at 510, which is still bigger than 360. So I'm going to subtract 360 again, and I'm going to find out it's at 150. So where's 150? It's over here in the second quadrant. Let's make that look nicer. There we go. So here's my triangle, here's my reference angle, theta. Well, if I'm at 150 and the x-axis is 180, the reference angle must be 30. Remember, in radians, that's pi over 6. Now let's use reference angles again to help us out here finding trigonometric functions of certain angles. I want to find the sine of 240 degrees. Well, this is easy because 240 degrees is already between 0 and 360. So if I make my little coordinate plane, 240 degrees is going to be here in the third quadrant. So I'm going to ask myself, should my answer be positive or negative? All students take calculus. In the third quadrant, sines are negative. Now, I'm going to find the reference angle because that's going to help me determine what the solution is. Well, if this is at 240 degrees and this is at 180 degrees, the difference between them is 60. So the reference angle is 60. Well, at 60 degrees, my ordered pair where the terminal ray hit the unit circle was at 1/2, comma, square root of 3 over 2. This is the sine. So the answer must be negative, square root of 3 over 2. Now let's do this again in B. Well, 495 degrees is not between 0 and 360. So I'm going to first find a coterminal angle to make my life a lot easier. So this is going to be the same as the cotangent of 135 degrees. That's much easier to deal with. 135 degrees is in the second quadrant. Here's my triangle. The reference angle is 45. which means that this is my ordered pair, where 45 degrees hits the unit circle. Next question, should the answer be positive or negative? Well, only sine and its reciprocal are positive in quadrant 2. Everything else is negative, so tangent must be negative. Negative what? Well, tangent is the reciprocal of, cotangent is the reciprocal of tangent. So if tangent is sine over cosine, then cotangent must be cosine over sine, which means it's 1 over the square root of 2 over 1 over the square root of 2, which is 1. And since it's in quadrant 2, the answer must be negative 1. Remember, if it helps you out, if you're dealing with angles and radians and you want to change them into degrees, that'll also help you find the final answer. You don't have to change it into degrees, though, but you can if it's more helpful to you. So I want to find the sine of 16 pi over 3 and the secant of negative pi over 4 using reference angles. Well, I know the reference angle here is pi over 3 and the reference angle here is pi over 4. But the question is, where was the original angle at? That's where changing it to degrees might help you out. So let me start with this. I already know that if the reference angle is pi over 3, which is 60 degrees, this is my ordered pair where it hits the unit circle. And for pi over 4, I know this is where it hits the unit circle, but it's now going to depend on what quadrant we're in. Let's go to B for a second because that's easier. Negative pi over 4 is in the 4th quadrant because you start in standard position and you go clockwise. In the 4th quadrant, are secants positive or negative? Well, secant is the reciprocal of cosine. And cosine's positive, so secant must be positive. So the answer is going to be positive reciprocal of cosine. The cosine is 1 over the square root of 2. Its reciprocal is square root of 2 over 1. Now let's go back to A. 16 pi over 3 is larger than a full circle. How do I know? Well, because a full circle would be 2 pi. So that would be 6 pi over 3. So what I'm going to need to do to figure out what quadrant it's in is to keep subtracting full circles until I figure out where 16 pi over 3 actually lies. So I'm going to subtract 6 pi over 3, which is going to give me 10 pi over 3, which is still larger than a full circle because I said a full circle is 6 pi over 3, which is 2 pi. So now I'm going to subtract another 6 pi over 3, and I'm going to get 4 pi over 3. Well, now I know what quadrant that's in. It's in quadrant 3. How do I know? Because 3 pi over 3 is at 180 degrees. So 4 pi over 3 must be a little past that in quadrant 3. So now in quadrant 3, are sines positive or negative? They're negative. So the answer is going to be negative sine of that reference angle. So it must be negative square root of 3 over 2. In section 5.2, we also introduced these reciprocal identities and the Pythagorean identities. And we're going to review them one more time because they're worth it. So cosecant's the reciprocal of sine, secant's the reciprocal of cosine, cotangent's the reciprocal of tangent. Those you already know. Tangent we defined as sine over cosine, so cotangent must be cosine over sine. The Pythagorean identities were sine squared theta plus cosine squared theta equals 1, tangent squared theta plus 1 is equal to secant squared theta, and 1 plus cotangent squared theta is equal to cosecant squared theta. So let's do some manipulations of these identities. In part A here, I want to express sine theta in terms of cosine theta. And I want to remind you that one of these identities said the sine squared theta plus the cosine squared theta is equal to 1. Well, if I want to express sine in terms of cosine, that means I want sine to equal something with a cosine in it. Well, I can take this equation and I can subtract the cosine squared theta. And then I can square root the other side. And notice I have the plus or minus symbol. The reason I have the plus or minus symbol is because if it's positive, square root of 1 minus cosine squared theta, that means that it must be in quadrants 1 or 2, because those are where your signs are positive. If it's negative, square root of 1 minus cosine squared theta, it must be in quadrants 3 or 4, because those are where our signs are negative. In part B, I want to express the tangent of theta in terms of sine theta, where theta is in quadrant 2. That means I want tangent theta to equal something that only has signs in it. Well, if you start with this equation for tangent, the numerator already has a sign. I wonder if I can rewrite the denominator so it only has a sign. Well, I can use the same theory that I used in part A by using this particular Pythagorean identity, but instead solving it for cosine. So first you would subtract the sine squared theta, and then you would square root the other side. But now we have to decide, should I pick positive or negative square root of 1 minus sine squared theta? Well, oops, I should not have a cosine squared. It should just say cosine theta is equal to plus or minus 1 minus sine squared theta. All right, let's try that again. So, we're in quadrant 2. Is cosine positive or negative in quadrant 2? It's negative. So in the denominator, I'm going to replace cosine with negative square root of 1 minus sine squared theta. And that would be tangent written in terms of sine. I'm going to do this example different than the method in the book. If you want to find out how the book did it, feel free to read their example number 6 on page 458. But I like my version better. If tangent theta is equal to 2/3 and theta is in quadrant 3, find the cosine of theta. Well, I know my terminal ray is in quadrant 3, so I'm going to draw it over here, and then I'm going to make my triangle. Here's the reference angle. If that's theta and theta is 2/3, that means the side opposite is 2 and the side adjacent is 3. Now remember, this is in quadrant 3, so really these are both negatives. But when you have a negative divided by a negative, they become a positive. In order to find the cosine, which is adjacent over hypotenuse, I'm going to have to find the hypotenuse. Well, using the Pythagorean theorem, negative 3 squared is 9, negative 2 squared is 4, 4 plus 9 is 13, square root of 13 is my hypotenuse. So the answer must be negative 3 over the square root of 13. If you want to rationalize it, you can tell me it's negative 3 square root of 13 over 13, but you don't have to. If the secant of theta is 2, and theta is in quadrant 4, find the other 5 trigonometric functions of theta. Well, if you know the secant is 2, its reciprocal is cosine, so the cosine must be 1/2. It's the other 4 that I'm going to need to find. And what I'm going to start with is drawing a picture of a triangle in quadrant 4. So here's my coordinate plane. Here's my terminal ray in quadrant 4. So here's my triangle with theta over near the origin. The secant is really 2 over 1, and the cosine is 1/2. Cosine is adjacent over hypotenuse. So in order to find the other 4 trig functions, I'm going to have to find the opposite side using the Pythagorean theorem. So 1 squared plus y squared is equal to 2 squared. So y squared is equal to 4 minus 1 is 3. Y must be the square root of 3. Should it be positive or negative, though? Well, in quadrant 4, this should be negative. So the sine is going to be negative square root of 3 over 2. Cosecant is negative 2 over the square root of 3. Tangent should be negative square root of 3 over 1. Cotangent will be negative 1 over the square root of 3. We can use trigonometry to help us find areas of triangles. Now you already know the formula for the area of a triangle is 1/2 the base times the height. Problem is you need to know the base and the height. And in a triangle, the height is always a right angle or a what do they call it? I forgot what they call it, but the height's always perpendicular with the base. Now, there's another formula in trigonometry that we can use for finding the area, and I'm not going to derive it for you, but I'm going to give it to you. It's going to be the area is 1/2 AB sine theta. Let's say that this is theta. Then these two sides would be A and B. The way the area formula works is it's 1/2 two sides of a triangle times the sine of the angle between them. It's a side angle side property that you use when finding the area. And I just remembered we call that an altitude. So the height in a triangle is always an altitude to the base. Let's find the area of triangle ABC. Now I said in order to find the area using that formula, you need a side, an angle, and a side. As long as you have that, the area is 1/2 the product of the two sides times the sine of the angle between them. Well, this is going to be 1/2 of 30, which is going to be 15, times the sine of 120. Well, the sine of 120 is the same as the sine of 60, because that's its reference angle, and the sine of 60 is the square root of 3 over 2. So the area is 15 square root of 3 over 2 square centimeters. That's the exact value. You can tell me the approximate answer, which is approximately 13 square centimeters.